Section 4.2 talks about the addition rule and multiplication rule. I'm going to break this section into two lectures. I'm going to assign the homework. I'm going to split it up among the two sections as well. So I want to separate between you getting this probability of compound event before I go on and get the conditional. So you need to understand this before we could do the conditional, which is why I'm doing half of the section. So a definition, a compound event is any event combining two or more simple events. Notation, the probability of A or B denotes the probability that event A can occur or event B can occur or both. And the formula for it, probability of A or B, most books denote that by union. You don't have to worry about that in this book. That's the probability of A, probability of B, but by adding A and B, you might have added the same amount or the overlap twice. You subtract that, and is denoted in most books by intersection, meaning the probability of event A or B is the sum of each event occurring individually minus the probability of both occurring at the same time. Probability of A and B, again that's intersection, denotes the probability that A and B both occur at the same time. Now a Venn diagram is very useful to really get this idea out of the way. Two events are disjoint or mutually exclusive if they cannot occur at the same time. There's no way they could happen at the same time. In the event that A and B are mutually exclusive, probability of A and B would be 0. So, we're going to leave this blank for now. We come back to it. If we're dealing with a disjoint, disjoint events look like this. There's nothing common between them. Call this event A. Call this event B. So the probability of A and B, well, there's nothing common between them. Versus if I look at A, you know what? Let me stick with the same coloring. If I call this event A, call this event B. So let me do that and show you how that works. If I say, what's probability of A and B, well, that would be this part. That doesn't equal 0. Right? And according to the formula that we have, probability of A or B, here it's a probability of A plus the probability of B. If you subtract the probability of A and B, well, that's 0. That really doesn't mean much. But here, if I say the probability of A or B is the probability of A, notice what I'm counting. I counted all of those. Plus the probability of B. Do you see which part I counted twice? I counted one time when I did the green, and I counted one time when I did the green, the blue. I counted this twice. That's why I would subtract it once, so I don't overcount. And here we are. Determine whether the following are disjoint. Disjoint means events that cannot happen at the same time. So, a coin lands on heads. A coin lands on tail. Well, those are disjoint. Why is that? There's no way you could flip a coin it could land on both heads or tails. Here's another event. Event A, you pick numbers 1, 2, 3, or 4. Event B, you pick numbers 2, 3, 5, or 6. Here, do you see that this is not disjoint? Why is that? Because they have those in common. The probability of A and B is not 0. And to demonstrate that with an example like we just did, notice how this would look. If I draw event A, and the best way to do this is to put them first and start with the overlap. Start with what's common. What's common is 2 and 3. If this is A, then all what I need is 1 and 4 there, and if this is B, I would need 5, 6, or 7. And if I say look at event A, wouldn't you say all of these are A? If I say look at event B, wouldn't you say all of these are B? And do you see which part I would count twice if I just add those? The overlap of yellow and blue is green. Alright, how about here? A person plays soccer. A person plays baseball. This is not disjoint. Why is that? Well, because you could have a person that plays soccer and plays baseball at the same time, right? One person could do that. Here, you roll a die, you roll an even number. Even means what? 2, 4, or 6. You roll an odd 1, 3, or 5. Could you roll a die and get a number that's even and odd? That's disjoint. They cannot happen, or mutually exclusive, whatever you prefer. Now comes the actual use of it. Well, let the probability of event B be 11%, F be 78%, G be 56%. The probability of F and G together is 42%. And event E and F are disjoint. That means they can't happen at the same time. Meaning probability of E and F is 0. That can't occur at the same time. Find the probability of F or G. According to the formula up there, probability of A or B. The probability of A plus the probability of B minus the probability of both. So according to the formula, probability of F plus probability of G minus the probability of F and G. Probability of F is 78%. Probability of G is where's G? 56%. Minus the probability of F and G, that is 42%. If I plug this in my calculator, I will get a 0.92, which means what? So here again, if you want to see it, 0.78 plus 0.56 plus minus 0.42, 0.92, or 92%. Find the probability of E and F. That's the probability of E plus the probability of F minus the probability of E and F. Probability of E is 11%. Probability of F is 78%. Probability of F and G, they didn't give me that because they told me it's disjoint. It's really 0. If I add those, that's 0.89. Again, if the problem doesn't specify, you could leave the answer as decimal. You could write it in percentage, whatever you like. We're going to apply the same analogy now to cards. So those of you that are not familiar with cards, here they are. We have 4 suits in any deck, right? We have 2 colors, and we have 4 of each, 4 aces, 4 2, 4 3, 4 4. The cards are in order except for aces. They could count as high or low depending on the problem. We're not going to do any poker or anything like that, so you don't have to worry about that part. We're just going to do basic probability. And what is that? Basic probabilities of simple events or compound events. There are 13 each. So there are 52 cards in a deck. And here it says, suppose that a single card, one card, is selected from a deck of 52, such as shown below. This is the deck. What is the probability of drawing a king? The probability of a king. How many cards are there? There are 52. How many of those satisfy the king? They're right there. 1, 2, 3, and 4. So those 4. Now, on a test, you're done right there. Not a problem. You want to get me a decimal? By all means. And if you want to plug it in and give me the percentage, I can care less which of those 3 you give me. Any one of them will do. If the problem says write it in one form, you should be able to. Now I reset the problem, and let me look at the next case. The next case says, what is the probability that the card, the one card, is a king or a queen? I have 2 ways of doing this, and I'm going to do it both ways for you. I could say that's the probability of a king plus probability of a queen minus probability of a king and a queen. Probability of a king, there are 52 cards, so 4 of those. Probability of a queen, there are 52 of those, 4. Again, or is a choice you add. Minus, can you pick a card that's both a king and a queen? Well, that's not possible. So the answer is 8 out of 52. That's a fine answer, right? Which is roughly 15.4%. Or I could say there are 52 cards in a deck. King or queen? Well, king or queen, that would be 1, 2, 3, 4, 5, 6, 7, 8. You're welcome to do that if you wish. Doesn't really matter. You should be accustomed to both. And what is the probability that the card is drawn is a jack or red? That's the probability of a jack plus probability of a red minus the probability of a jack and red. Again, I'll show you both ways of doing this. First case, you say, okay, probability of a jack, there are 52 cards. How many ways can you get a jack? There are 4 of those. They're right there. Plus probability of red, there are 52 cards. How many of them are red? 13 and 13, that's 26. Minus, how many cards are red and jack? Do you see I have those 2? And in this case, you will get what is that? 30. 28 out of 52. That's a fine answer. 53.8%. Or I have 52 cards. I want a jack or red. I do the counting myself, jack or red. If I do the counting myself, I wouldn't overcount, meaning red 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, right? 27, 28. If I count myself, there's no way of counting those 2 twice because I see them and I'm doing them one at a time. So you could do that too. Now, of course, you're not going to do that by hand. You can start imagining doing that, and it works, really. Now I want to look at what is the probability that the card is an odd number or a heart. That's the probability of odd plus the probability of heart minus the probability of odd and heart. The probability of an odd number, 52. How many are odd? 4, 8, 12, 16, 20. Kings and queens and jacks are not considered either or. And out of 52, how many are hearts? How many are hearts? Out of 52, 13 are hearts. How many did I overcount? Can you tell which ones I counted twice? Well, look. Didn't I count this twice? Once when it was a heart, once it was an odd. So do you see I counted 1, 2, 3, 4, 5 of them? Twice. And in that sense, I'll be getting out of 52, 5, 15, 28, which is 53.8%. Of course, there is another way of doing this, and let me show you that. I could say out of 52 cards, I'm going to do the counting by hand. Meaning what? Meaning, let's see how this works. If I take, let's see, this color. I want to know what's the probability of an odd or heart. Well, let's start with the hearts. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. You'll notice if I'm doing the count, I wouldn't count this twice, which is what this does. So visually, it's very helpful to see. Sometimes the cards are a bit overwhelming, so the formulas will do. Whatever you like to use, you could use. And here's our second example. A study of 1,000 recently deceased people is summarized in the table below. Here we go. If I split those, and separate them completely, I'm going to do this both ways using the formula and visually. If I add those, that's 200. So 2 people died from cancer. From heart disease, 10, 300 people. From other diseases, 10, 11, 10, 500. So altogether, I have 1,000 people. If I was to ask how many people died that smoke, 100, 280, 400, which means this must be 600 because they must add up to 1,000. And let's do this quickly. Find the probability that a randomly selected person, someone died from cancer. There are 1,000 people. How many people died from cancer? Well, that would be all of those, which is 200. Or 20%. What is the probability that someone did not die from cancer? That's the complement of cancer. That's anything but cancer. Well, there's 1,000. Think of it this way. If 200 people died from cancer, 800 are left. That's the easiest way out. Or you could do the counting. You could say, well, that is 180 plus 120 plus 120 plus 380. But think of it this way. If the probability of not passing a test is 20%, then the complement of that is passing. If 20% is not passing, that means 80 would be passing. Same analogy. How about here? What is the probability of someone who died of heart disease and cancer out of the 1,000? Heart disease and cancer. Heart disease is right there. Cancer is right. There's no overlap. According to the study, none. And the probability that someone who died from heart disease or cancer out of 1,000, heart disease or cancer. Oops, that's not what I meant. Heart disease or cancer. Heart disease, there are 300. Cancer, there are 200. That's 500. That's 50%. Right? Of course, I could say that's the probability of H plus probability of C minus the probability of H and C. This is 300 out of 1,000. This is 200 out of 1,000. And this is 0 out of 1,000. You could do that too, if you wish. All right. Almost there. E. Someone who smoked or died of heart disease. I could do the counting, or you could say somebody that smokes, somebody who died from heart disease, minus the probability of a smoker and died of a heart disease. So again, you have that option every time. So if I go by this technique, smoker or heart disease, smoker, 100 plus 180 plus 120, that's 400, right? Or heart disease, 400 plus 120 is 520. That's 52%. If I want to go by this, probability of a smoker, let me reset the numbers. Probability of a smoker probability of a smoker, that's 400 out of 1,000. Probability of heart disease, how many people have heart disease? 300. Smoker and heart disease. A smoker and heart disease. That's 180. There's 180 that I counted twice. And if you plug this in a calculator, you will get 700 minus 180, which is 520. And there it is. On the homework sheet, you're going to go in section 4.2 and you're going